Hey guys, this is David. In the last two lectures, we have learned how to derive the constraint equations for both Revolute and translational joint. In this lecture, we will show you how to derive the constraint equations and how to analyze the displacement of a slider crank mechanism. First, let's take a look at the slider crank mechanism. Just by first sight, it is easy to tell that this mechanism consists of four rigid bodies, three revolute joints, and one translational joint. Note that the reason why T1 exists is because rigid body 3 is translating on the ground. With this information, we can conclude that this mechanism is a single degree of freedom system. By now, this should be a piece of cake for you, but since this is a good practice, it is more than suggested that you post the video first and see if you do end up with the same result. Next, since now we are using Cartesian coordinates, we need to define the global coordinates of the system and the local coordinates of each rigid body. Here, I have set the origin of the global coordinates at point O, so as the origin of the local coordinates of the ground, and let theta 0 denote the angle difference between the local coordinates of the ground and the global coordinates. As for the local coordinates of the rest of the rigid bodies, they are defined as this. Since each rigid body needs three coordinates x, y, theta to describe its position and orientation in the global coordinates, we end up with 12 coordinates or 12 degree of freedom if we will. But since this mechanism is a single degree of freedom system, therefore we need to derive 11 corresponding constraint equations to reduce the degree of freedom of the system from 12 to 1. In the following slides, I will show you how to derive them one by one. Okay, let's first start with the constraint equations for the ground. Generally, we usually assume that ground doesn't move. Therefore, its coordinates x0, y0, and theta 0 should always remain constant. And in this case, it happens that x0, y0 are at the origin of the global coordinates, and that the orientation of the ground in the global coordinates, theta 0, is 0. Therefore, we can easily derive these three constraint equations shown here. Next, we are going to derive the constraint equations for R1, R2, and R3. But before that, let's have a quick review on what we have learned about Revolute Joint. Here, a point P1 on rigid body 1 and a point P2 on rigid body 2 are joined together by a revolute joint, which means the position of P1 and P2 in the global coordinates will always be the same. Therefore, we can express their position using coordinate transformation and derive the constraint equations shown here. First, let's focus on R2, the revolute joint between rigid body 1 and rigid body 2. Since point B is a point on both rigid body 1 and rigid body 2, therefore we can define two local vectors S1b and S2b in the local coordinates of rigid body 1 and rigid body 2. In this example, they are -50, 0 and 100, 0, respectively. With these two local vectors, we can express the position of point B using coordinate transformation and end up with the constraint equation shown here. And if we expand them, we will have the constraint equations shown here. Next, for R1, the revolute joint between the ground and rigid body 1. Basically, the procedure is the same as R2, except that the position of the ground x0, y0 is identical to point O. Therefore, the local vector S0O is just 0, 0. And again, with these two local vectors, S10 and S0O, we will be able to come up with these two constraint equations. Last, for R3, the revolute joint between rigid body 2 and rigid body 3. Since the procedure is identical to R1 and R2, so I'm going to leave this one for you to practice. Pause the video first and check the answer after you are done. If you are correct, you should come up with these two constraint equations. Okay, now we are done with all the revolute joints and the only joint left is the translational joint T1. And again, let's do some quick review on what we have learned. Recall that in this example, rigid body 2 is translating on rigid body 1. In order to derive the position constraint for the translational joint, we have defined 3 points that are on the translational axis, which are point A, a point on rigid body 1, and point B and C, 2 points on rigid body 2. Since these 3 points will always be on the translational axis, we can then rely on this geometric property to derive the position constraint equation shown here. Okay, now back to our slider crank mechanism. Here, rigid body 3 is translating on the ground. In order to derive the position constraint, we again need to define 1 point on the ground and 2 points on rigid body 3. However, note that the position of the ground and rigid body 3 are identical to point O and point C respectively, and since they are already on the translational axis, therefore we only need to define one more point on rigid body 3. Here, I have defined point D to be another point on rigid body 3, and its position in the local coordinates of rigid body 3 is 100, 0. Now, with these 3 points, O, C, and D, we will be able to come up with the position constraint equation shown here. As for the angle constraint, since rigid body 3 is translating on the ground, the angle difference between rigid body 3 and the ground should remain constant, which in this case is simply 0. That's why we can come up with the angle constraint shown here. Okay, so this is how we derive the constraint equations for the slider crank mechanism. And in order to solve for all 12 coordinates, we need to define one more equation, which is the driving link constraint, to specify the value of one of the coordinates. With the driving link constraint, we will decide the way how the mechanism moves. Usually, for this slider crank mechanism, we will either rotate rigid body 1 or push rigid body 3 back and forward to make the mechanism move in a certain pattern. Namely, we usually set rigid body 1 or rigid body 3 to be the driving link. And to do so, we need to specify a function of time, dt, to decide the way how rigid body 1 rotates or how rigid body 3 translates. If we express this mathematically, we can obtain these two equations. So, what exactly is dt? It really depends on you. You get to decide how rigid body 1 or rigid body 3 moves. Here, I'm going to show you two examples. For the first example, rigid body 1 will start to rotate from initial angle theta 1 init with initial angular velocity omega 1 init and angular acceleration alpha 1. As for the second example, rigid body 3 will start to oscillate from initial x position x3 init with amplitude 8 and frequency omega 3. And if we move everything to the left-hand side, we will end up with these two constraint equations for driving link. Now we have 12 equations and 12 unknowns. And after these equations are solved using MATLAB, we will end up with the position of all the rigid bodies. So this is how we derive the constraint equations of a slider crank mechanism and how we analyze its displacement. In the next lecture, we will show you how to analyze the velocity of the same mechanism. See you next time!